The Bessemer converter didn't look dangerous. It looked like a giant egg, a squat iron vessel sitting on pivot points inside a Pittsburgh steel mill. Then it tilted, and the sky inside the building turned white. 20 tons of liquid metal at 2,900 degrees were throwing a column of white sparks 30 feet into the air, showering everything within range in glowing slag while men worked 10 feet away. But what made the Bessemer truly dangerous wasn't the visible fire. It was what nobody saw coming until it was already moving. If you watch Steel and Sweat for the machines and the men behind the American industrial era, subscribe now and drop a comment telling me which industrial machine or disaster you want covered next. This channel exists to make sure these stories don't disappear. Andrew Carnegie heard about the Bessemer process while on a trip to England in 1872. He was already rich from railroads and iron, but he understood immediately what he was looking at. An English inventor named Henry Bessemer had patented a method for turning pig iron into steel in 20 minutes flat. Not the old way, which took days of skilled labor and produced small batches, but at scale, cheaply, and fast enough to feed the railroads that were eating up the continent. But the Bessemer process had not started cleanly. When Henry Bessemer first ran his experimental converter in a shed behind his office in London in 1856, he had no idea what he had built. The first 10 minutes of the blow had been quiet, gases rising from the top of the vessel, sparks floating off the way they do when you tap a furnace, ordinary industrial fire. Then the silicon and the iron burned out, and the carbon caught, and the converter became something that Bessemer later described as a veritable volcano in a state of active eruption. Molten slag and white-hot metal were thrown into the air. The apparatus rocked from explosions. Nobody could approach it to shut off the air blast. The roofs of nearby buildings were at risk of catching fire from the shower of red-hot material falling on them. Bessemer himself feared for his life. His first experiment had worked. It had also nearly destroyed the building, and the experience left him understanding that he had invented something that could not be operated carelessly, which is the kind of insight that becomes critically important once you put the machine inside a building and surround it with men on 12-hour shifts. Carnegie came home from England and built the Edgar Thomson Steel Works in Braddock, Pennsylvania, just outside Pittsburgh. And in August 1875, the first American Bessemer converters made their first blow. What the men on that floor would have seen was this: a vessel the size of a small house tilting forward, a ladle pouring a river of orange glowing pig iron into its mouth, the vessel tilting back upright, the air blast opening as soon as it settled. For the first several minutes, nothing alarming, just a column of sparks and hot gas rising from the converter mouth, and the low roar of compressed air moving through molten metal, a sound described by men who heard it as something between a blast furnace and distant thunder. Then the color shift. The orange sparks brightened and multiplied as the silicon burned away and the carbon caught. The roar increased. The flame at the converter mouth went from red to yellow to the white that Hawley described as dazzling. A full-spectrum light that threw violet shadows everywhere and made the gray Pennsylvania rain outside look beautiful blue through the windows. Men who had worked blast furnaces for 20 years had never seen light like that inside a building. A British observer writing about an 1856 demonstration documented the spark column reaching 30 feet at a pressure of 10 pounds per square inch, falling in thick showers across 12 to 14 square yards. The first American commercial converters ran at higher pressures and larger volumes. What came out of the top of a Carnegie converter was proportionally bigger, louder, and hotter. The men on the floor had been told what to expect, but being told and standing inside it are different categories of experience. What came out of those vessels would eventually become the frame of the Brooklyn Bridge, the rails of the Transcontinental Railroad, and the skeleton of every skyscraper that changed the American skyline. But in August 1875, what Carnegie had was a brick building in Braddock, a converter crew that had never run this specific machine before, and a process that had proven in its inventor's own workshop capable of burning the roof off the building it was inside. Before any of that steel reached a bridge or a railroad, it was a building full of fire and noise. Men in leather aprons had come to Pittsburgh from Poland, Croatia, Slovakia, and the American South because the mills were hiring, and the mills were the only game in town. What those men were signing up for, even if none of them fully understood it on the first day they walked through the mill gate, was a working life inside one of the most dangerous industrial environments that had ever existed anywhere on Earth. Here is what the Bessemer converter actually was. Picture a vessel shaped like an oversized pear, made of iron plate and lined inside with a heat-resistant clay material called refractory brick. It was mounted on two heavy steel axles called trunnions, which meant it could be tilted, like a ladle being poured, by a system of gears operated by the converter crew. At the bottom of the vessel, arranged in a ring, were a series of small holes called tuyères. Compressed air was piped in through those holes at high pressure. The vessel held anywhere from 8 to 30 tons of liquid iron, depending on the size of the installation. Carnegie's converters at Edgar Thomson held about 7 tons each, and he ran them in pairs. When you were ready to make a blow, you first tilted the converter sideways and poured the molten pig iron in from a giant ladle suspended on an overhead crane, a ladle that itself weighed several tons and glowed a dull orange from residual heat. You did this carefully because if the ladle lurched or the chain slipped, you had a river of liquid metal moving across the mill floor. The iron temperature coming out of the blast furnace was roughly 2,600 degrees Fahrenheit. Not hot enough yet for the process to complete. But once you had the iron inside the converter and you stood the vessel upright and opened the air blast, the temperature rose on its own through a process that still seems counterintuitive, even if you understand the chemistry of the Bessemer process. The compressed air forced through the bottom tuyères carried oxygen with it, and that oxygen reacted violently with the carbon and silicon dissolved in the pig iron. Carbon oxidizing in a bath of liquid metal is not a gentle chemical event. The reaction is exothermic. It produces heat rather than consuming it, and that heat is generated inside the metal itself, distributed through the entire molten mass at once. In the first 10 minutes of a blow, you would watch sparks and hot gases rise from the converter mouth, and the experienced men on the floor could tell by the color and texture of the sparks exactly what stage of the process they were in. Orange and coarse sparks meant carbon was burning. As the carbon content fell, the flame changed from orange to bright yellow to a white so intense it was painful to look at directly. Then sometime around the 15-minute mark, the carbon ran out. When the carbon ran out, the flame simply died. Not gradually. It stopped suddenly, cut off as if a switch had been thrown. That was the moment. You had maybe 60 seconds to cut the air blast, tilt the converter, and pour the steel into the waiting ladle before over-oxidation ruined the whole heat. The converter crew worked by signal and by sight, and by the kind of muscle memory that only comes from having done the same thing hundreds of times, in conditions loud enough to make shouting useless, and hot enough to blister exposed skin from several feet away. The 1865 eyewitness account by Alexander Hawley, one of the American engineers who brought the Bessemer process to the United States, describes the mill floor during a blow as a cavernous room where the sounds of suppressed power were melancholy and deep. Lurid beams of light flashed in your face as some remorseless beast opened its jaws. A column of air, compressed solid like rods of glass by the power of 500 horses, pierced and shattered the iron at every point, chasing it up and down, and was itself hurled out in roaring blaze. Hawley was a trained engineer trying to describe the process accurately. Even he ran out of technical vocabulary and started writing about monsters and beasts. That is how it looked, and that is what it sounded like, and that is what the men who ran it heard and saw for 12 hours at a time. McClure's magazine sent a writer to the Edgar Thomson works in 1893, 18 years after the first blow, by which point the converter operation was smooth and routine enough that it had happened thousands of times without incident. And still, the writer described the result as a ferocious geyser of saffron and sapphire flame streaked with deeper yellow, from which a light streamed that flung violet shadows everywhere, and made the gray outside rain a beautiful blue, a fountain of sparks that arose gorgeous as 10,000 rockets and fell with a beautiful curve like the petals of some enormous flower. That is what was happening inside the building while the men worked. The spark column documented from an 1856 demonstration rose to a height of 30 feet and fell in thick showers across an area of 12 to 14 square yards. 30 feet is the height of a 3-story building. The sparks were droplets of liquid slag traveling through the air and cooling as they fell, most of them extinguished before they hit anything. But the ones that landed on a man, on his collar, or through the gap at his wrist or down the back of his neck, those ones burned through to skin before you could get them off. The workers on the converter floor wore leather aprons and sometimes leather hoods, but the heat made heavy protection impossible to wear for the full 12 hours. You learned to stand at the angles that kept your face out of the direct spray. You learned which way the draft moved the spark shower on different kinds of days. You learned it the way everyone learned everything in the mills, by doing it until you understood it in your body or until something went wrong. The converter floor had its own hierarchy and its own knowledge system that existed entirely outside any written record. The first helper, the second helper, the blower, the melter, the vessel man, each had a specific role and a specific position and a specific set of signals they used to communicate, because the noise of an active blow made speech useless at any distance beyond arm's reach. The experienced converter crew could run a blow in the dark based on sound alone, tracking the roar of the reaction and the character of the flame, reading the color shift from yellow to white with the same precision a doctor uses to read a pulse. This knowledge was not taught in any formal sense. It lived in the crew, passed from man to man by working alongside each other through thousands of blows, and when a man was killed or disabled and had to be replaced, that specific knowledge went with him, and the new man had to earn it back from the beginning. Things went wrong regularly. In 1893, a steelworker at a Pittsburgh mill described his workplace this way: "They wipe a man out here every little while. Sometimes a chain breaks and a ladle tips over and the iron explodes. Sometimes the slag falls on the workman. Of course, if everything is working all smooth and a man watches out, why, all right. But you take it after they have been on duty 12 hours without sleep and running like hell, everybody tired and loggy, and it is a different story. If you have made it this far in this video, hit subscribe right now and leave a comment about which piece of American industrial history you want to see covered next. Every comment helps this channel reach the people who care about these stories." The ladle tip the worker described was one of the specific nightmares of the Bessemer operation. The overhead ladle on its crane held 7 or more tons of liquid iron or liquid steel, depending on where in the process you were. If the rigging failed, if a pin sheared or a chain link fractured from the repeated thermal cycling, the ladle dropped. 7 tons of liquid metal hitting the concrete floor of a mill bay does not pour. It explodes. It spreads outward in a disk of fire and sprays burning metal across everything within range. The specific hazard of the mill floor was that the area around the converter was never empty. There was always a crew present during the blow. There had to be. Someone had to watch the converter, watch the flame, work the tilt mechanism, signal the ladle crane. There was no way to do the job and also be somewhere safe. But the ladle drop was not even the worst scenario. The worst scenario was liquid steel contacting water. Steel at 2,900 degrees and water, even a small amount of water, produce a steam explosion so violent and so fast that the men who witnessed them and survived described it as an artillery shell going off inside the building. The physics are simple. Water vaporizes into steam at 212 degrees Fahrenheit. At 2,900 degrees, the conversion is essentially instantaneous. Water expands by roughly 1,700 times its volume when it turns to steam. If that expansion happens inside or immediately beneath a mass of molten steel, the steam has nowhere to go but up and out, carrying the steel with it as a projectile spray. Every ladle had to be thoroughly dried before each pour. Every mold had to be preheated. A patch of condensation on a floor the steel was about to cross was a potential bomb. The entire discipline of Bessemer mill operations, the preheat routines, the inspection protocols, the specific way the ladles were handled and stored, was built around the problem of keeping liquid steel away from any surface that might hold moisture. And still, across the decades the process ran, steam explosions happened in American mills. They happened because the mill ran all the time. They happened because men worked 12-hour shifts, and tired men made small errors, and in the converter shop, small errors had no margin. They happened because the equipment cycled through brutal thermal stress thousands of times, and metal fatigues, pins fail, chains crack through in the night, and by the time you know it has happened, the ladle is already moving. Fatal accidents in steel mills accounted for 20% of all male deaths in Pittsburgh in the 1880s. A newspaper account from the period described the yearly lists of men killed and wounded as being as long as a casualty list for a small battle in the American Civil War. The sociologist John A. Fitch, who studied the Pittsburgh steel industry in the early 1900s, coined the phrase "old age at 40." By that age, if a man had not been killed outright, his body was typically finished for heavy mill work. The heat, the lifting, the 12-hour days without real breaks, the sudden temperature changes moving between the furnace heat and the outside air, accumulated damage that expressed itself as joint failure, respiratory problems, and a kind of physical exhaustion that did not respond to rest, because the rest was never long enough. One Homestead laborer put it plainly in 1894. You do not notice any old men here. The long hours, the strain, and the sudden changes of temperature use a man up. A plate mill worker named William McQuaid described his shift in 1893 by saying the only stop was the time it took to oil the engine, a pause of 3 to 5 minutes, during which some of the men ate if they had thought to bring food at all. Many had not, because they had not got time. Another worker described losing 40 pounds in his first 3 months from the furnace heat, drinking 2 buckets of water across every 12-hour shift, the sweat dripping through his sleeves, running down his legs, and filling his shoes. Carnegie gave his workers one holiday per year, the 4th of July. The rest of the year they were in the mill. The average steel worker in 1890 earned approximately $10 a week. At that wage, Carnegie himself earned the equivalent of roughly 4,000 of his workers. The men who stood next to the Bessemer converter and watched the 30-foot spark column and kept the blow running on time were earning money that put them just above the poverty line in a city whose air was so thick with industrial smoke that gas streetlights burned at noon. The 3 rivers running through Pittsburgh had the color and texture of sludge. The men who made the steel that built the country breathed the air that steel making produced, lived in the neighborhoods closest to the mills because they could not afford to live anywhere else, and sent their sons to the mill as soon as those sons were old enough to be useful. In 1892, those men tried to formalize what they had. The Amalgamated Association of Iron and Steel Workers was one of the largest unions in the country, and Carnegie's Homestead Mill was one of its strongholds. When the contract came up for renewal and Carnegie's partner Henry Clay Frick cut wages and demanded concessions, 3,800 workers refused the terms. Frick locked them out, built a 12-foot fence topped with barbed wire around the mill property, and hired 300 Pinkerton agents to retake the plant by barge on the night of July 5th. The workers were waiting for them on the riverbank. The firefight that followed lasted all morning. 7 workers and 3 Pinkerton agents were killed. The Pennsylvania governor eventually sent 8,000 National Guard troops to hold the plant while strikebreakers took over the work. The union was destroyed. Organized labor would not return to the American steel industry until 1937. The workers went back to the converter floor on Frick's terms and Carnegie's schedule, 12 hours a day, 7 days a week, $10 a week. The Bessemer kept blowing. The process began to be replaced by the open hearth furnace in the 1890s and the 1900s. Open hearth furnaces were slower, but produced higher quality steel and allowed for better chemical control, which became more important as the products steel went into became more demanding. The Bessemer process had an inherent limitation. The blow was so fast, typically 20 minutes, that there was almost no time to sample the steel and adjust its composition mid-process. You were essentially committing to whatever the iron's chemistry gave you and correcting afterward. The open hearth process took 6 hours per heat, But those 6 hours allowed for sampling and adjustment that produced more consistent results, which mattered enormously once steel was going into structural applications where the engineer specifying the material needed to know exactly what it would do under load. But the Bessemer era, roughly 1875 to 1900, was when American steel production went from a curiosity to the dominant industry on Earth. United States commercial production of Bessemer steel went from roughly 10,000 tons in 1869 to 1 million tons in 1880, and the price fell by half in that same period. By 1900, the United States was the largest steel producer in the world, and the city of Pittsburgh was at the center of it. The Bessemer converter was the machine that made that happen. By the 1930s, the Bessemer was largely obsolete in American steelmaking. The last commercial Bessemer heat in the United States was run in 1968. The only operating Bessemer shop in the world today is in the Ural Mountains of Russia. But the period of roughly 1875 to 1900 was when the machine mattered most, and when the men who ran it paid the highest price. Those were the years when the American rail network was being built, and the American skyscraper was being invented, and the American industrial city was taking the shape it would hold for the next century. All of it built on steel. All of that steel was made in a process that involved a 20-foot egg-shaped iron vessel, compressed air blown through holes in the bottom, and a column of white fire rising 30 feet in the dark of a brick building while exhausted men watched the color of the flame and waited for it to change. The men who ran the Bessemer converter are in aggregate now a percentage of Pittsburgh's male death rate in a given decade, a line in a sociologist's book about old age at 40, a quote in a labor history about chains breaking and ladles tipping. What they made is still holding weight. The steel from Carnegie's Bessemer converters at Braddock and Homestead is inside structures that are still standing. Bridges they never crossed, buildings they never entered, a country they helped build with their hands from the inside of a brick mill in Pittsburgh, standing 10 feet from the machine, watching the sky turn white